So welcome to the second module on calculus. In this video, I'm going to talk about partial derivatives and implicit differentiation, which are tools for multivariable calculus, which sounds awful. But all I mean is, up till now we've dealt with functions of a single variable, usually x, right? So, it's always been f of x is equal to some thing to do with x. Multivariable equations are just that, functions of multiple variables. Maybe it's a function of x and y, so it's going to be x squared plus y squared plus 3xy, or something like that. Most interesting things in the real world, especially in population biology, tend to be functions of more than one variable. At any given moment, your probability of dying in the next 10 minutes is a function of your age, your sex, various health things, random luck. Many different variables go into determining outcomes. So most of the time, you're going to be dealing with functions of multiple variables. So we're going to talk about how to take derivatives of those functions. So remember, if I had some function f of x, the derivative of f prime of x, tells me the rate of change of the value of the function as x changes. Now what if I have some other function g of x and y, how do we define a derivative for a function of two variables? There's no single one, right? Because if I define the derivative of g to be how the value of g changes as x changes, then we're ignoring the effects of y. And if I say I want to know how g changes as y changes, then we're ignoring the effects of x. So there's no single derivative of g, but it has two partial derivatives, which we typically write as g with respect to x of x and y is the partial derivative with respect to x, which is how g changes as x changes. Or we can write g of y, the other one, partial derivative with respect to y. Sometimes we also use this squiggly d, dg by dx, and dg by dy. It's still just a derivative. We use the squiggly d so that we know it's a partial derivative, not a single variable function derivative. So looking at that same function, g of x and y, which I think I said was x squared plus, x squared plus 2y minus 3 is my function. And I want to compute the partial derivatives of g, of which there are two. Any function that has n variables is going to have n partial derivatives, right? Because you can change any one of the variables. So it's pretty much the same as taking a regular derivative. It's just for each partial derivative, we're treating all the other variables as constants, which makes sense, right? Because if I want to know the rate of change of the value of g as x changes, we're assuming all of the other variables remain constant, so we can kind of ignore them, right? So by that token, the partial derivative with respect to x, well, the derivative of 2x with respect to x, well, here we'll write it out this way. For every term, it's the derivative with respect to x of x squared plus the derivative with respect to x of 2y minus the derivative with respect to x of 3. That makes it fairly obvious, right? The derivative of x squared with respect to x is 2x. The derivative of 2y with respect to x is 0, because y is a constant in this context, and 3 is also a constant. So similarly, the partial derivative with respect to y is the derivative with respect to y of x squared plus the derivative with respect to y of 2y minus the derivative with respect to y of 3. Which again, that's a constant, so we just get 2. This particular example isn't terribly interesting because x and y are acting independently to affect the value of g. What ends up being really interesting and what happens in most applications is that there'll be some interaction between x and y, and the partial derivatives will help us tease that apart. So let me show you with an example. With fish, because I like fish. You will notice there will be a lot of examples with fish. I used to be a marine biologist, that's my bias. I like fish examples. So let's say you have an aquarium, and it's got some fish in it. But you're a scientist, and it's got some plants in it. Because aquarium fish like plants. There's some bubbles. There we go. My fish have blue eyes. Anyway. You've got a collection of aquarium goldfish, and you've been taking really careful observations of their mortality rates over the years, and you've come up with a model that describes the mortality rate of your goldfish as a function of their age and as a function of how many aquarium plants are in the tank at the time. And you want to know how many plants you should have in your tank to keep your fish alive the longest. Okay, so let's define some variables for my example. So A is going to be the age of the fish in question. P is going to be the number of plants in the tank. I'm going to assume each plant is the same size and contributes the same amount of oxygen in space. It's an oversimplified model. It's just an example, so assuming. And we're going to call M the probability of death in the next year over some time interval. Yeah? Okay. So my imaginary mortality function is going to be M is equal to 0.2 a squared of 200 plus P minus 20 over 400, all squared, minus 2 times A times P over 800. Now, my imaginary mortality function is such that mortality will increase with age, and it will have a sort of parabolic relationship with plants, such that having too few plants increases mortality, and having too many plants increases mortality. Because too few plants, maybe they're not making enough oxygen, maybe there's not enough to eat. If there's too many plants, maybe there'll be a space issue, not enough space for the fish, or they might have too much oxygen. I had a fish die that way once, it was very sad. And then this third term at the end makes there be some interaction between age and plants. So maybe older fish need fewer plants so they have more space, say. Anyway, so I want to know how mortality changes as age changes, which means I want the partial derivative of mortality with respect to age. So that's going to be dm by dA, which is going to be d by dA of the first term plus d by dA of the second term minus d by dA the interaction term. So the first term, the derivative of 0.2a is 2 times 0.2a, which is 0.4a over 200. d by dA of the second term just goes away because p is a constant. Right, this is the derivative with respect to a. And in the final term, we just get minus 2p over 800. Because the derivative of 2 times a times p with respect to a is just going to be 2p. And the other partial derivative, I want to know how mortality is going to change if I add another plant. Well, that's going to be dm by dp, which is d by dp for the first term, plus d by dp of the second term, oops, that should be 400, minus d by dp, the final term, which I'm running out of space here. Well, the first term, right, 0.2a squared over 200 with respect to p, that's just going to be 0 because a is a constant. The second term, we're going to get 2 times p minus 20 all over 400. And the final term, we're going to get d by dp 2ap over 800. That's just going to be 2a over 800. So we see in both cases, right, the effect on mortality of adding a plant is going to depend both on the number of plants I have already and how old the fishes are. So now, even though we haven't talked about optimization yet, I'm going to do a quick optimization to show you why these partial derivatives might be useful. Let's say I know that all the fish in my tank are 2 years old, and I want to know how many plants I should put in their tank. So I want to minimize the mortality risk to my 2-year-old fish. So I can take my expression for dm by dp and say, where is it 0? So I mentioned before, the actual relationship between mortality and the number of plants, right, looks kind of like this. Because if you have too many plants, mortality is high. If you've got too few plants, mortality is high. So there's some sweet spot number of plants down here. And if you look at the derivatives of this function, at the minimum, the derivative is 0. The tangent to that function is 0. So I'm going to solve my partial derivatives for where the derivative of m with respect to p is 0, and that's going to give me minimum mortality, the number of plants that gives me minimum mortality. It's a bit of a skip ahead to the next module, but anyway. So if I want dm by dp to equal to 0, well, when age is equal to 2, then that gives me, I want 2 times p minus 20 minus 2 all over 400 to be equal to 0, which gives me 2p minus 40 minus 2 is equal to 0, p is equal to 22. And what about for older fish? Let's say my fish are all senior citizens. I got them from a fish rescue, say. Fish rescue. In that case, we've got 2 times p minus 20 minus 10 is equal to 0, 2p minus 30 is equal to 0, p is equal to 15. So for young fish, the optimum number of plants is 22, but for old fish, the optimum number of plants is 15. Meaning maybe the young plants need more shelter, I don't know what. My point is, partial derivatives can tell you a lot about your function, especially if there are interactions between your variables as to how they affect the outcome. One last thing to know about partial derivatives, although really all you need to know about partial derivatives is that they're just the same as regular single variable derivatives, but you have to remember to treat all the variables except the one you are deriving with respect to treat the other ones as constants. And because partial derivatives are just like single variable derivatives, all of the rules work for partials too. The product rule, the quotient rule, the chain rule. I'll just show you quickly. So the product rule, let's say I've got some function z of x and y, which is equal to a product of two other functions of x and y. Then the derivative of z with respect to x is going to be the derivative of g with respect to x times the other function plus the derivative of h with respect to x times the other function. Right? Looks just like the product rule for single variable functions. The same as if instead z is a quotient. Oh, and the same sort of rule will apply if I was deriving with respect to y, right? It would be just the derivative of g with respect to y times the function plus the derivative of h with respect to y times the function. Same thing. So back down to the quotient, right? Quotient rule applies, same way. dz by dx is just going to be dg by dx times h minus dh by dx times g times g of x and y all over h of xy squared. Just like the quotient rule for single variables, just with funny shaped d's. So, right, that's the product rule. And that's the quotient rule. All of the rules work. Right? And it doesn't matter how many variables your functions have. These could be functions of 3, 4, 5, 6 variables. It would work the same way. So the other multivariable thing I wanted to talk to you about today was implicit differentiation. So if I'm going to talk about implicit differentiation, I should tell you what I mean by implicit versus explicit. If I have a function y is equal to f of x, some function of x, then I've written y explicitly as a function of x. But if I have, say, x squared plus y squared equals 2x minus 3, I haven't written y explicitly as a function of x, but it still is a function of x. It's just implicitly a function of x, if that makes sense. So if I wanted to take the derivative of this function, say, I could do it two ways. I could rearrange it, so you get y squared is equal to 2x minus 3 minus x squared, which means y is equal to the square root of all that stuff. And then I can find an expression for, oops, I'm still doing partials. Then I could find dy by dx in the usual way. Or I could just take the derivative of everything without rearranging. And that's called implicit differentiation. So over here, I'll do implicit differentiation on this one. So I want to find the derivative with respect to x of all this stuff, which gives me, just like I did, kind of like I did for partials, right? It's d by dx, the first term, plus d by dx, the second term, plus d by dx, right? All the stuff on the other side, which just means, well, d by dx of x squared is going to be 2x, and d by dx of 2x minus 3 is just going to be 2. Now what do I do with this? This doesn't look too friendly. So we kind of have to chain rule this, by which I mean it's going to be d by dx of y squared is going to be the derivative of y with respect to y, 2y, times the derivative of y with respect to x, dy by dx. And then I can just rearrange it so that the dy by dx is on its own over here, which means dy by dx is equal to 2 minus 2x all over 2y. And since I want this all in terms of x, I can substitute 2 minus 2x over 2 times this value of y over here, 2x minus x squared minus 3. So I can check that, right? I can check over here. I can do it the other way around, the usual way. dy by dx of this business is going to be 1/2 2x minus 3 minus x squared times the derivative of the inside, which is just 2 minus 2x, which ends up being 2 minus 2x all over 2 times the square root of the ugly stuff. Okay. So implicit differentiation is just a different looking way of getting at the same result. So implicit differentiation gets you the same answer as regular differentiation. You just do the rearranging after you take the derivative instead of before. So I'm just going to do one more example to make sure you kind of get what I mean here. So let's say my function is y to the power of 5 plus 3x to the power of 6 times y is equal to 2x minus 3 again. This time, I can't rearrange it to get y by itself on one side, right? There's y in two different terms, and they're two different powers. I can't write y explicitly as a function of x, so I have to use implicit differentiation. And honestly, most of the time I do differentiation implicitly anyway because I am lazy, and I may as well do the rearranging at the end. So if this seems odd to you, I'm going to do a little brain trick that I use to make implicit differentiation make more sense, is I'm going to rewrite this as y of x, as a function of x. All my y's are y as x now, so y is a function of x to the 5th plus 3x 6 times y of x is equal to 2x minus 3. It just reinforces that y is a function of x. It makes the chain rule aspect of this make more sense to me anyway. So now if I want my derivatives with respect to x, then I'm taking d by dx of y of x to the 5 plus d by dx of y of x times 3x to the 6th, which is equal to d by dx of 2x minus 3. So now to compute those derivatives, well, for the first term, d by dx of y to the x 5th, we chain rule it, so we get 5 times y of x to the 4th times dy by dx. And for the second term, I'm going to need the chain rule because I've got two functions in there, y of x and x. I'm going to do that in blue and put big brackets around it so it's clear. So product rule, f prime times g plus g prime times f. That's how I think of it. So we want the derivative of our first function, which is just dy by dx, times the second function, 3x 6th, and then plus the first function, y of x, times the derivative with respect to x of the second function, which is going to be 18 times x to the 5th. And then d by dx of 2x minus 3 is still 2. So first we end up with dy by dx times 5y 4th plus 3x 6th, all equal to 2 minus 18x to the 5th times y of x. So our final answer, dy by dx is equal to 2 minus 18x to the 5th y, all over 5y to the 4th plus 3x to the 6th. You couldn't have done that with regular differentiation. We had to do it implicitly, but it's pretty straightforward. I hope you agree. So in summary, partial derivatives are just like regular derivatives. But treat all the variables as constants except the one you're deriving with respect to. WRT is short form for with respect to in math land. And for implicit differentiation, all you're really doing is deriving first and rearranging later. So thank you for listening to this brief introduction to multivariable calculus, the most useful kind of calculus since everything in the real world depends on more than one variable. Everything interesting does, anyway.